Let's find the sum of the fourth powers. In particular, I want to calculate the sum, n goes from 1 to k, of n to the fourth. Now, playing with this analogy, I could think about this problem the same way that I'd approach an integration problem. I should try to anti-difference n to the fourth. I should try to find a list of numbers whose successive differences are n to the fourth. To try to find a list of numbers whose differences are n to the fourth, let's just try to find some lists of numbers and their differences. So as a first example, let's take a look at, say, n to the fifth, and let's look at the fifth powers. So 0 to the fifth is 0, 1 to the fifth is 1, 2 to the fifth is 32, 3 to the fifth is 243, 4 to the fifth is the same as 2 to the 10th, that's 1024. 5 to the fifth is 3125, and so on. So that's just lists of fifth powers. Now let's try to find the differences between subsequent numbers in this list. So the difference between 1 and 0 is 1. The difference between 32 and 1 is 31. The difference between 243 and 32 is 211. The difference between 1024 and 243 is 781. And the difference between 1024 and 3125 is 2101, and so forth. Now, it's maybe not so helpful just to see specific numbers. Let's try to write down a formula for this. So I'll write the differences between the fifth powers. Well, that's n to the fifth minus the previous fifth power, so minus n minus 1 to the fifth. And then I could expand this out. I could take n to the fifth minus this thing expanded, and I'd get 5n to the fourth, because the n to the fifth will cancel, minus 10n cubed plus 10n squared minus 5n plus 1. Right? And the plus 1 comes from subtracting a minus 1 to the fifth. Okay, so that formula there gives these green numbers. It's the differences in the fifth powers. Now I'm going to play the same kind of game for a different list of numbers. Let's try to find the differences in the list of, say, fourth powers. Well, that'll be the fourth power of n minus the fourth power of the previous number of n minus 1. And again, I can expand this out, and n to the fourth minus, there's an n to the fourth here that cancels. So the highest power that survives is an n cubed term with a coefficient of 4 minus 6n squared plus 4n minus 1. So this formula tells me the differences between subsequent fourth powers. Now I want to combine those to get something with the difference of n to the fourth. Okay, but how am I going to do that? Well, here's something I could do to make it a little bit easier to see what's going on. Instead of looking at differences between fifth powers, I could look at the differences between 1/5 of fifth powers, right? That has the effect of dividing all these numbers by 5. And since all these coefficients, except for the last one, are multiples of 5, that'll make that formula look a little bit nicer. And I could do the same thing with n to the fourth. Instead of looking at fourth powers, I could look at 1/4 of fourth powers, and that'd have the effect of dividing all of these coefficients by 4. So let me just write down, what we've got here and summarize the resulting formulas. So the differences between n to the fifth over 5, well, according to this, that'll be n to the fourth minus 2n cubed plus 2n squared minus n plus a fifth. And I get a similar kind of formula for looking at differences of n to the fourth over 4. It's this divided by 4, and that'll give me an n cubed minus 3/2 n squared plus n minus 1/4. Well, let's just try to combine those two. But how exactly do I want to combine them? Well, the deal is that I've got an n to the fourth here, and that's really what I want at the end of this process. I want something with the differences n to the fourth, because I'm trying to anti-difference n to the fourth. Then I've got a minus 2n cubed, and I've just got an n cubed here. So if I took this and added 2 copies of this, I'd be in pretty good shape. So what would I get in that case? It would be looking at the differences of n to the 5th over 5 plus 2 copies of n to the 4th over 4, and that would give me an n to the 4th. The n cubed term would go away. I'd get a minus n squared, because I've got a 2n squared minus 2 copies of 3/2 n squared. And then I get a plus n, because I've got minus n plus 2 copies of n. And then a 5th minus 2 copies of 4th will give me minus 3/10. I could try to get rid of that n squared term by adding on the differences of n cubed. Well, why does that work? Well, if you calculate the differences for the list of numbers n cubed over 3, you end up getting an n squared minus n plus a third. So if I take this and add this, that'll get rid of this n squared term, right? So I'm going to look at the differences of n to the 5th over 5 plus 2 copies of n to the 4th over 4 plus n cubed over 3. And I'm left with an n to the 4th. No more n squared anymore. The plus n minus n also cancels. And then I've got minus 3/10 plus a third. And that ends up being plus 1/30. Now I can get rid of the 1 over 30th term. Now how do I do that? Well, look at the differences of the list of numbers n over 30, and that's just 1/30th, right? This list of numbers, each number in that list differs by 1/30th compared to the previous number in the list. So if I take this and subtract n over 30, then the differences in that list are exactly n to the 4th, right? By which I mean that I take d of n to the 5th over 5 plus 2 n to the 4th over 4 plus n to the 3rd over 3 minus n over 30. And then I've got n to the 4th plus a 30th minus a 30th, and what I'm left with is just n to the 4th. So in light of all of this, what do I know right now? Taking differences between a list of numbers and this accumulation function, adding up the first k numbers on the list, those are inverse operations, right? This is the discrete version of the fundamental theorem of calculus. In this particular case, the differences between these numbers give you the 4th powers, so if I sum the 4th powers, I get this, at least up to some constant. Now I just have to worry about that constant. But that constant is 0. We can check it. Here's a sum from n equals 1 just to 1 of n to the 4th. And I can just plug in any value of k that I like. Since this constant c doesn't depend upon k, I can figure out what that constant is by looking when k equals 1. So this is just 1. But on the other side, I've got what I get when I plug in k equals 1, which is 1/5 plus 2 times a 4th plus, 1 to the 3rd over 3, so plus a 3rd, minus a 30th, plus that constant c that doesn't depend upon k at all. But a 5th plus a 1/2 plus a 3rd minus a 30th is 1. So I've got 1 equals 1 plus c, so that means c equals 0. And that tells me what the formula then for the sum of the 4th powers is. It's just this, and that constant is just 0. This whole process is really analogous to the fundamental theorem of calculus and how we use it, right? In this example, I'm anti-differencing n to the 4th in order to sum n to the 4th. In the same way that if I were to anti-differentiate x to the 4th, that would help me to integrate x to the 4th, right? This analogy runs really deep.